All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. I left you guys with an example to do last time. So let's actually just jump into that. Let's make sure I can see that. Right. So the main thing I want to talk about today is optimization. But we have a curve sketching problem left to do from last time. So we're going to go through that. Hopefully you tried it. I'm going to go through it somewhat quickly, but it is it's the same success process that we looked at before. And even the question here states everything that it wants you to do, except the domain, which we'll normally find anyway, just to make sure that whatever points we find, they're actually on the graph and we can actually plot them and they're actually what they appear to be, like a max or a min or an inflection or something like that. But you always need to find the domain because it turns out if something is not in the domain of the original function, like there's an asymptote or a hole, those points will also always be critical points, right? So the derivative doesn't exist where the function is undefined, right? So you will need to know these points because they're going to show up in your critical points list. And you want to know that you're not allowed to touch these points, right? So we always start with the domain. So here, it should be clear that we cannot touch -2 and we cannot touch 2. So that's the domain, everything except -2 and 2. Right? X squared minus 4 becomes 0 when x is plus or minus 2. Okay, so that's fine. Moving on, the next thing we try to find is the intercepts. And someone's coming in here. So there are two we care about. There are the x-intercepts, which remember you set y equals 0. And there are the y-intercepts, which you set x equals 0. So for the x-intercepts at y equals 0, this means x squared over x squared minus 4 equals 0. This, of course, means x squared equals 0. This means, of course, x equals 0. Write it down here. Remember, a fraction is only 0 if the numerator is 0. And you just need to make sure that whatever makes the numerator 0 does not make the denominator 0 at the same time. And yeah, that x equals 0 does the job. So that's the x-intercept. Of course, now we look at the y-intercept where we set x equals 0. So this means your y would be 0 squared over 0 squared minus 4, which is, of course, 0. So y equals 0 is your y-intercept. Okay, cool. Moving on. Ugh. Come on, iPad. Okay, 3, we would like to find the asymptotes. Remember, we care about two kinds of asymptotes. There is the horizontal asymptote, and we know how to find those. You're going to find the limit as x approaches infinity of our function, and you're going to find the limit as x approaches negative infinity of our function. We know that if it's not top-heavy, these will give us the same answer for rational functions. However, you probably don't know that in the beginning, so you just write down both of them at the same time. It shouldn't be too bad to get them. So what is the limit as x approaches infinity of this guy?
One.
It's 1. And this would also be 1 by ratio of leading coefficients. So now this means that y equals 1 is a horizontal asymptote. Remember, if either of these limits give you a constant, that is a horizontal asymptote. Now we look at the vertical asymptotes. And for this, we just have f equals x squared over x squared minus 4. We check that it's reduced, which means we can just set denominator equals 0, at which point we would get x squared minus 4 equals 0. So your x equals 2 or your x equals minus 2. And those guys are your vertical asymptotes. Move on to the fourth section. In this section, we figure out where the function is increasing, decreasing, where it hits maximums and minimums. We do this via the first derivative test. For problems of this type, I will always give you the derivatives because, you know, on a test where you're doing this, I would have already tested your ability to do the quotient rule and take derivatives and things like that. So I don't want to waste your time doing it with a complicated problem like this, where you have to do the quotient rule twice just to move it. I just want to know, if you know the derivative, do you know what to do with it, how to use it? So here we know that we would use the first derivative, which is given to us, and you don't need to verify it when it's given. Right? The problem would even say that you need not verify. That's it. So now we're going to find the critical points. So this means that f prime equals 0 or f prime undefined. Clearly it's undefined if x equals plus or minus 2, and f prime equals 0 means x is 0. So we have 3 points to test in the first derivative. So there's 0, minus 2, plus 2. Pick random numbers in between them, minus 3, minus 1, 1, 3, and you plug into the derivative. I want you to notice that in the derivative, we have a square in the denominator, which means as long as it's not 0, it is going to be positive. So I know I'm always going to be dividing by a positive here. So I only have to look at the numerator to see how this thing is going to behave. So if I plug in a negative number into minus 8x, I would get a positive number. If I plug in a positive number into minus 8x, I will get a negative number. So these will give me positives, which means I'm increasing. And these will give me negatives, which means I'm decreasing. Now, what is 0 in this case?
Maximum.
It's a maximum. How do we know it's a maximum? You're increasing on the left, you're decreasing on the right, and 0 is in the domain. So the function is continuous there. 0, come on, iPad. 0 fits in this interval right here. So it's in the domain, and we're increasing on the left, decreasing on the right. So this guy gives us a max. We need to find the coordinate for the max, which means we need to find f of 0, but we know that's 0. So that's just 0, 0 is the coordinate of the maximum. The maximum, there's a maximum point that occurs at the origin. Minus 2 and plus 2 are nothing because they aren't in the domain, but honestly, they wouldn't be anything anyway because you're increasing on both sides for one of them and you're decreasing on both sides for the other one. It wouldn't be a max or a min either way, but they're definitely not anything now because they're not even in the domain. So we can summarize this step because we were specifically asked for these things. So we always have to show that we're finding them. We can talk about the increasing, decreasing, maximum, minimum. Notice that we're increasing from negative infinity to negative 2 and then negative 2 to 0. We're decreasing from 0 to 2 and 2 to infinity. And maximum, we have one at the origin. Minimum, we have none. So that's this section right here. And of course, hopefully it's obvious, but I do want you to remember that these guys are intervals, while these guys are points. Right, so I'm using interval notation. So it can look like a coordinate. So like that -2, 0 in the very top line, it looks like a coordinate. It's not a coordinate. It's an interval, right? So when you're doing the increasing and decreasing, those guys are intervals. So now we'll move on to the fifth step. Here's where we look at concavity. So where are we concave up? Where are we concave down? Where do we have inflections? That's all taken care of in the fifth step. They're all taken care of by the second derivative, which here we were given is 8 times 3x squared plus 4 over x squared minus 4 cubed. So now we're going to find critical points. We know that we need f double prime equals 0 or f double prime undefined. This again is obvious to be plus or minus 2. F double prime is 0. Well, there's no solution to that, right? Because 3x squared plus 4 is not equal 0 ever, right? X squared is going to be 0 or positive. So that expression is always going to be bigger than positive 4. And then you're multiplying it by an 8. It's never going to hit 0, right? It's completely above the x-axis. So the only critical points for the second derivative are the -2 and 2. And we can plug in a random number here, random number here, random number here. Notice that the numerator of the second derivative is always positive. So we only need to check what the denominator is doing. If I plug in -3 into x squared minus 4, that's 9 minus 4, that's positive. If I cube it, it's positive. Plugging in 3 would do the same thing because it's an x squared. So I know that's going to be positive as well. What about plugging in 0? You get 0 squared minus 4. That's a negative. If you cube it, you get a negative. So here we have a positive. We have a positive. We have a negative in the middle. In the second derivative, positive means concave up. Negative means concave down. So we have that going on. You want to know that this is not an inflection since not in domain. Same thing goes for this guy. So there's nothing to say here in terms of inflection points. We don't have any. So under normal circumstances, if -2 or 2 was in the domain, these would be inflection points because that's where we switch concavity. We switch from concave up to concave down. So at -2, we switch from concave up to concave down. At 2, we switch from concave down to concave up. However, they're not in the domain, so they are nothing. We will move on to stating the summary here. Where are we concave up? Where are we concave down? Where do we have inflections? So we're concave up on -∞ to -2 and 2 to infinity. We're concave down in between that. Inflection points, we have none. That's the summary from the fifth part. And again, these are intervals, and these would be actual points on a graph. Now we move on to the sixth step, where we actually do the graph, right? And we're going to summarize all of this on it. So let's actually kind of set that up here. So there we have the x-axis, we have the y-axis. And now remember what we put in first. We're going to put in all the coordinates that are important. So things like the x-intercept and y-intercept, which here there's only one, that's 0, 0. That's an intercept, the origin. All right, what other points would we have besides intercepts? We would want to know if they're max or mins. There's a max at the origin. No inflection points. So there's only one point given to us here, and that's the max. Okay. After we put in all the important coordinates, we are going to want to put in the asymptotes. So we go to the asymptote section. We have horizontal asymptotes at y equals 1. We have vertical asymptotes at x equals 2 and x equals -2. So there's an asymptote here. This is y equals 1. That's an HA. And then we have vertical asymptotes. Here. Here. So this is x equals -2. It's a vertical asymptote. Here's x equals 2. It's a vertical asymptote. So you put in the asymptotes next. After that, we start putting in the intervals. So we can start with the intervals of increasing and decreasing. You'll see here, we are increasing from -infinity to -2 and then -2 to 0. So this is -2. From -infinity to -2, we're increasing. We're also increasing from 2 to 0. Then we're decreasing from 0 to 2. And then we're decreasing from 2 to infinity. That is kind of lean, isn't it? No idea if that's a little better. Okay, so that's increasing, decreasing, decreasing. Okay. Now we're going to put in our intervals of concavity. We're concave up on -infinity to -2 and from 2 to infinity. So on the ends, and we're concave down in the middle. So we're concave up all the way here, as well as all the way here. And we're concave down in the middle. Now we've put all of this on the graph. We can essentially just stop looking at what we wrote earlier. Everything we need to graph this guy is on the graph. And so now you can start graphing. And to help you, one way is to plug in points, but another way is to just check in each region if it makes sense for the graph to be there, and you can figure it out from there. So for example, if I look on the right side, can the graph be down here? And the answer would be no, because if I'm supposed to be decreasing and that's a vertical asymptote, it would have to do something like that, which would create an x-intercept, which we know there are none here. So the graph cannot be down there, right? Because if it obeys all the other rules I gave it, it will create a contradiction. So the graph cannot be down there. Okay. Can the graph be in this region? Well, no, for a couple of reasons. Again, it will have to do this to meet that. However, it will have to be y equals 1. It would have to settle at y equals 1 for the horizontal asymptote, which means it would have to do that. Now, if the graph does that, what you would notice happens is you will create a minimum. You will create a local minimum by doing that. We know there's no local minimum because we tested it, so that's not possible. So it turns out the graph must be up here, entirely up there, entirely in the top right corner. That's the only option. So what would it have to look like? Well, it has to obey the vertical asymptote and the horizontal asymptote. So it'll look like this. Entirely in the right corner. Notice that it is decreasing, concave down, concave up. It's shaped like a smiley face. It approaches the asymptotes it's supposed to approach. It's decreasing. It fits all the features that we found earlier. There is no contradiction with what I found earlier. In any other region on the right side, I would have made a contradiction. By a similar token, the left side is going to look exactly the same, just a reflection. I don't know if that looks exactly the same, but it should. Okay, and it keeps going up and keeps going to the side. All right, so now we're in the middle. Okay, could we be up here? Well, the answer is no, because this is going to be the max. Could we be in here? The answer is no, because this is going to be the max, right? It can't be anywhere there. It has to be entirely down here, right? So your graph has to be entirely underneath the x-axis because we hit the max at the x-axis. So now I look in here, I notice that I'm increasing over here. I'm increasing concave down, so I shape like a frowny face while moving up. I will also notice that I'm decreasing over here, and I'm still concave down, so I'm like a frowny face. So you'll notice that it looks, I mean, when you draw it on the picture, it'll look like a parabola, but it's not really a parabola because parabolas don't have asymptotes. But it essentially will look like, on the scale, like an upside down parabola. But it's stuck inside the asymptotes. You'll notice that on the left side, it's increasing concave down. Once it passes the y-axis on the right side, it's decreasing concave down. So that's the graph. That fits everything. Right. So that is that. Practice a lot more with curve sketching. Luckily, you won't have to be explaining to anyone how to do it and what to test, so you'll be a little faster. But you practice and you should be able to get through these in 15 minutes tops. You don't want to take longer than that. All right. So moving on to the next section, I want to talk about optimization. Get in between here. Small, maybe I'll make that a little bigger. Hopefully I can. And then move this under here. Okay. So we're going to talk about optimization. And this, I believe, I want to say it's section 4.6, I want to say. 4.6, optimization. As always, handouts can be found on class webpage. But in these handouts, they kind of tell you everything you want to know. I like typing these sections up because the problems are going to be word problems and I don't want to have to write these out. But if I'm going to write out the problems, I might as well write out the steps. So the handout will tell you everything you need to know, but we're just going to go through it very quickly and then actually jump into trying to solve some problems. So optimization, what is optimization about? Well, optimization is one of the most important applications of calculus. I mean, the other one is for linear approximation. These are super duper important applications. What optimization is, or what it means to optimize something, is to make it as good as possible, as good as it can be within certain restrictions, right? And that's it, right? Which I know it sounds very vague. However, mathematically, you can make this precise in the sense that as good as it can be often means maximizing or minimizing something. So if you're running a business and you're looking at profits, what's the best thing? Well, you want to maximize your profits. What is the maximum profit I can make? Or if you're looking at costs, you would tend to want to minimize costs. What is the minimum costs I have to pay? And things of that sort. So there are times when what's the best possible scenario comes down to you maximizing or minimizing something. And whenever that's the case, optimization via derivatives is one way you can go. Now, there are other ways to do optimization without calculus, but it's a calculus class, so I'm going to tell you the calculus way to optimize stuff. But there are situations in which calculus won't work, obviously. So want to make something as good as it possibly can be, but the idea is we have restrictions, and that's always going to be the case because we don't have infinite resources. So there's always going to be something that's in short supply, right? Relatively speaking. So you can be the business owner who wants an infinite amount of profit, but you don't have an infinite amount of employees. You don't have an infinite amount of offices. You can't make an infinite amount of products, sell it for an infinite amount of money, right? There are restrictions. You only have this many employees, this many offices, this many products you can make per day, right? There's going to be a limit to how many things you can do. So given those limits, those restrictions, or what we call constraints is the technical word we will use, how can you make something as big as possible or as small as possible inside of those constraints? That is what optimization is about. Now, how do you actually go about doing that? And by the way, the point of optimization also kind of tells you when the word problem you're looking at is an optimization problem. So we know when a word problem is a related rates problem because they're going to describe related quantities. They're going to tell you the rates of change of some of them and then ask about the rate of change of another one. But with optimization, that's not how it's going to be phrased. Optimization is going to be phrased like they're going to describe a situation and then they're going to tell you to make something as good as possible, come out with the best scenario, or maximize something, or minimize something. That's going to be how it's phrased. It's not going to be phrased like a related rates problem, so you shouldn't actually mix them up. So once you read it and you realize that it is an optimization problem, everyone in this class can be solved with these 6 steps. I don't know what it is with 6 steps. We had 6 steps for related rates. We had 6 steps for curve sketching. We had 6 steps for optimization. It's just a coincidence. It's not on purpose. Like there's no reason that there are always 6 steps, but there are 6 steps. The first one, as always, is to read carefully. You want to read, make sure you understand the problem, because if you don't fully understand the problem, you won't know what to do. You probably won't even recognize it's an optimization problem in the first place. The second thing you should do, like in related rates, is to come up with a diagram, especially if equations aren't given to you. You want to draw a picture of the situation, make sure you can understand what's going on and how you want to go about it, right? And yes, you properly label this the same way you would always, right? And of course, formulas from geometry will come in handy here. Now, here's where we start to diverge from related rates. Everything else now is different. Here, we're going to set up two equations, not one equation. We're going to actually need two, because not only do we want to worry about one thing that we want to make as good as possible, but we also want to worry about the restrictions. You'll need an equation for each one. So an equation that describes your restriction or the constraints you're under is called the constraint equation. So you're going to come up with the constraint equation. That's the one equation that you'll need. This is the equation that describes your constraints or restrictions, right? Normally, the constraint is going to be the guy that its value is given to you. So to go back to the profits example, they would say something like, oh, you want to maximize profit, but you only have 500 employees. The fact that they gave you that number 500 tells you, oh, that's a limit, right? That 500 is very important. If you have an equation that can describe how to get that 500, that would be the constraint equation. So there's going to be something that's going to be given to you. You're not going to be able to choose the value. It's just going to be a value that's a matter of fact, like this is what you have. And so you can come up with an equation to describe that number. The second equation you're going to want to come up with is the objective equation. Now, this is the equation that describes the thing that you want to maximize or minimize, right? So it's your objective to make this as good as it possibly can be, right? So you actually need two equations here. Now, once you do that, what you'll usually notice is that your objective equation is going to have more than one variables in it, but we're in single variable calculus. So we only have one independent variable at a time. We're not in Calc 3, so that's no bueno. How you proceed then is to get a new objective equation. And you get that by solving for one of the variables in your constraints and plugging it into your objective equation. This will get your objective equation all in one variable. So now you have a function of just one variable that you want to maximize or minimize. We know how to do that. Derivatives. Find the derivatives, find the critical points, set it equal to 0. Technically, what you're going to want to do is find the absolute max. But it's usually not going to be the answer. You'll notice that most physical problems, they will not work out at the edges. It's possible that you can have a problem where it works out at the edge, but it's not very common. But I would consider it anyway, just because there will probably be a problem in your homework on that. But usually it's going to be a relative. Oh yeah, I did say that. In practice, it is often a local max or min that will solve your problem, right? And we'll see why the edges don't make much sense a lot of the times in our first example. Now, once you go through all that and you can find the maximum point, now you're left with step 6, which is to answer the question. So at the end of the day, a very specific question is going to be posed to you. How many of blah do we need? Or what is the blah that we would get, or whatever, right? They're going to ask you a very specific question, and you need to make sure that you answer that question. So it's not just good enough for you to find the answer in part 5. You have to show that you know how to interpret that number and answer the question in part 6. So yeah, once you go through those 6 steps, you would have solved the optimization problem with Calculus 1. Now, a very nice problem, I think, to illustrate this is problem 1 in the handout. I would recommend that you do all of them. At least I'm going to go through, I think, the first 5, which I guess we'll start today and that'll spill into next class. And then you can try 6 and 7 on your own if you want, which I would recommend. And you'll do it from the homework when I post the homework. I don't think I posted homeworks for anything after 4.3 yet. So I'll be sure to do that this weekend. Problem 1 is a very nice problem. It illustrates very nicely. In fact, usually when I'm in person, I do problem 1 while going through the steps and explaining the steps. But for us, because the handout is posted here, it's just easier to do it that way. Just read through it first. So now here's the problem. A farmer has 100 feet of fencing. He wants to make a rectangular enclosure. He wants the enclosure to encompass the maximum possible area so he can plant the maximum number of crops. What should the dimensions be? You should notice that this is not a related rates problem. It's not a curve sketching problem. It's not an exponential growth or decay problem. It's an optimization problem. Why? You're given a restriction. It's right here. We have 100 feet of fencing. You don't have an infinite amount of fence to make the biggest enclosure you want. You are given a constraint. You're also given an objective that you want to maximize. You want the maximum possible area. That is your objective. You want to maximize area. Then they ask you, what should the dimensions be? That is the question. At the end of the day, your final answer should be, the dimension should be this. The length should be this, the width should be this. If you do not make that statement, you have not answered the question, and you will of course lose points for that. Okay, so now we know this is an optimization problem. What do we do? Well, you go into the 6 steps, of course. The first one being to read, which we already did, read very carefully. The second one being we want to do a diagram. Now, we're told that he wants to build a rectangular enclosure. It makes sense to make the diagram a rectangle. A rectangle with unknown dimensions, because they're asking us the dimensions, right? So if I can make this X and that Y, make the length X and the width Y, right? Now, what you will notice here is that there are many possible scenarios, many possibilities here, right? So for example, he could build a rectangular enclosure where it's like 30 feet here, 30 feet there, 20 feet there, 20 feet there. And that's an enclosure with 100 feet of fencing. He could also do something like 40, 40, 10, 10. That could be a rectangle. He could do something like 25, 25, 25, 25, 25, right? He could do something like 35, 15, 15, 35, right? Etc. So there are many, many ways that he can build this. And this is just some of the integer options, right? He could do 33 and a half on the one side or whatever, right? So you need to find the best one. Right? That's what the optimization is, right? How can you make this as good as it can be? What is the best rectangle, right? That's what you essentially want to find out. That rectangle looked very freaky. So you draw a generic rectangle where you don't know the dimensions. All right, so now you move on to step 3, where you're going to have your equations. You're going to have a constraint equation. And you're going to have an objective equation. Right? Now, what you should recognize is that your constraint is what? How do you describe this in terms of geometry? The length of the fence. What would be the length of the fence according to this picture? What would that property be called? Notice that the length of the fence is the length around the rectangle. What is the length around an object?
Perimeter?
Perimeter, right, exactly. So you drawing that diagram, you know that all the lines you drew represents the fencing. So now you're told that, oh, we only have 100 feet of fencing, which means the length of the lines that you drew needs to add up to 100. That means the perimeter should be 100. So your constraint here is the perimeter of the rectangle. It cannot be whatever you want. It has to be 100 feet around. So we actually know how to find the perimeter. You just add up all the sides. So this means that 2x plus 2y must be 100. This is a constraint. In other words, your x plus y should be 50, right? That's your constraint equation. Now, what is the objective? Well, the question kind of said it plainly. You want to maximize area, which means an area function, an area equation should be your objective equation. So, of course, here with the rectangle, area equals length times width. So that's your objective equation. Notice that that is a function of two variables, x and y. That is no good. So that leads us to step 4, where we're going to get the new objective. How you do that is you solve for one variable in the constraint and you plug it into the objective. So we know that y is equal to 50 minus x from constraint equation. So this means your area equation is going to be x times y, right? Which is 50 minus x. So you solve for one variable in your constraint, you plug it into the objective. And that now is your area equation. Now you have the area equation and it's only a function of x. In fact, this is an inverted parabola. We know how to find the maximum, will just be the vertex. However, we are going to, there's a parabola. Max at vertex. So your x should be minus b over 2a, which is going to be minus 50 over minus 2. So we kind of know what it has to be, but we'll use calculus just to illustrate, right? But I know what the answer should be because this is a parabola. It won't always be a parabola, by the way, which is why you need to know all the steps. So now you have this function, your area is in terms of one variable. You can now go on to maximize or minimize. In this case, what we want is we want to maximize. So you just keep that in mind. You're looking for a maximum value. Now we know how to find the maximum value. You would need the critical points. So here you're going to find a prime. You're going to set a prime equals 0 or undefined. So here, this means that now a prime equals 50 minus 2x. So set 50 minus 2x equals 0 or 50 minus 2x undefined. Or you can just say, well, we know that's never undefined. You didn't even have to write that part. And here you would solve for x and you would get, look at that, 25. Now, some comments I want to make here. There is only one answer. It will be the right one in this class. So if you only get one answer, then that's the answer, right? Come on, it's not going to be anything. However, it's possible that you got several answers, right? This could have been a cubic or something like that. If you got several and the right answer isn't obvious, and do the first derivative test. Notice here, though, we do have limits. We can go anywhere from 0 to 100. So if we're worried about what x can be, it can be anything from 0 feet to 100 feet because we have 100 feet of fencing. However, notice that the endpoints don't make sense here, right? If you have 0 length, you didn't make a rectangle, right? So you'll notice here, the endpoints don't make sense. This is, I would say, typical. It's possible that the endpoints can give you the answer, but usually in problems like these, in the physical problems, they won't. So it doesn't make sense to give you 0 length because you won't have a rectangle. It also doesn't make sense to make all of the fencing be the length because then you would have 0 width and you wouldn't have a rectangle, right? So it doesn't make sense that the best solution will happen at the endpoints. It's not going to be where it happens. So chances are it's going to happen at a local point in between, which we now tested and saw it was 25. Now, if you tested that in A prime, plug in, say, 1 into A prime, you would get 50 minus 2, which is positive. So that would be positive, and you would be going up. And if you plug in like 26, you get like 50 minus 52. That's negative. So you'll have a negative on this side, and that will go down. Right? So you can see there that this is a max. Right? But if you only get like one answer, then I'm not going to expect to see you check. I'm just going to expect you to just, oh, that's the answer, and just move on to the next step. There are times when you have several answers where you don't need to check because one just won't make sense. So for example, in this situation, if you got a positive and a negative answer, you'll know to just ignore the negative answer. Like you can't have a negative feet amount of fencing, right? So there are times like that where you also don't have to check. However, if you got 2 positive answers, like you got a 25 and then a 50, whoa, which one is going to give me what I want? You have to test both of them, right? You have to do the first derivative test. One might be a minimum, the other might be a maximum. You might have several maximums. Like you're not going to have this in this class, but in theory, you could have several maximums, and you just need to check who's the biggest one. But yeah. So normally that check probably won't be necessary. But this leads us to step 6, where we have to answer the question. So what we want dimensions. And so that means you need length and width, right? So we know the length equals x equals 25. So this means that the width equals y equals 50 minus x, which is also 25. So then you can finally answer the question, what are the dimensions? Well, length 25 feet, width 25 feet. And this is how you would end the problem. That would be your final answer. But of course, you're going to show the work on how you got there. Another way to write dimensions, especially if it's like rectangles, rectangles are boxes. You can just do the multiplication notation. So you can say it's a 25 by 25 foot enclosure. Or, 25 by 25. There are many ways to state the same thing. Right? But you have to state that somehow. Now, I want you to appreciate that I didn't have to ask for the dimensions. I could have asked for what is the maximum area, in which case I would not need to even find the y. I know the x, I know the area equation, I could just plug that x into the area equation, and that answer would be the answer that I want, right? So you have to just be aware of what you're being asked and make sure you give that thing. And you may or may not need to solve for the other variables based on what you're being asked. So that's it. That's optimization. What I want you guys to do is to try the rest for next time. We'll try to knock out all of them. But we will end here. So try these. Again, these are the word problems, and ultimately, I don't think they are going to be. What I will say is they'd only be difficult if you don't put the practice in. Like these word problems like related rates, even curve sketching, optimization, things of that sort. The problems are the longer type, like you'll take a long time to write out the solution, but at the end of the day, each step should be relatively easy for you. It shouldn't be something that's difficult. If it's difficult, it means you just haven't practiced enough. You have to get used to going through the steps. So you want to practice until you know the steps by heart and you can know what to do next based on what you've done before. But try these for next time. And that'll be in the notes. And the handout is also on the class webpage. So yeah, we will stop there. Hopefully that was clear, and hopefully you have a good weekend. I will see you guys in the next one.